Serine is one of the 20 amino acids that's used to make a protein within the human body. Now, just like every other amino acid, there's a center carbon, the chiral carbon, the alpha carbon, the stereocenter carbon. The carbon has 4 different attachments. On an amino acid, there's going to be a carboxylic acid where there's a carbon, 2 oxygens, and one of those oxygens is attached to a hydrogen. It's also going to have an amino group where there's a nitrogen that's attached to 3 hydrogens that's attached to this carbon. This nitrogen should only have 3 total attachments, so the fact that it has 4 or this extra hydrogen attached to it means this is going to carry a +1 charge. Then it's also going to be attached directly to a hydrogen from the center carbon, and then the thing that makes every amino acid different is the R group that comes off of this center carbon. At the lowest pH possible, the fully protonated form is going to predominate, or the form where everywhere you could see a hydrogen, there you're going to see a hydrogen there. There's all kinds of extra hydrogen in the system, so this molecule can take as much hydrogen as it wants. As the pH goes up, or as the system starts losing hydrogen and this molecule has more hydrogen than the system does, this molecule is going to have to give up its hydrogen into the system in order to balance things out. The first hydrogen that's lost from this amino acid is going to come from this carboxylic acid group, and it's going to happen at a pH of about 2.2. So at 2.2, this oxygen is going to gain back its lone pair, and now this oxygen is going to have a -1 charge. This nitrogen is going to still carry its +1 charge, so this -1 and this +1 balance each other out to an overall charge of 0. And whenever you have a molecule where there's a negative charge and a positive charge, they balance out to 0, but there's actual formal charges on the molecule. It's called a zwitterion. And this zwitterionic form is what this molecule is going to look like all the way up until the pH hits about 9.2. At 9.2, the hydrogen that's on this amino group is going to be dropped, and that nitrogen is going to gain back its lone pair as well. And so now we've got this -1 charge from this oxygen. This nitrogen's back to neutral charge. So now this molecule overall has a -1 charge. And that happens after a pH of about 9.2. In the human body, which has a pH of about 7.4, that nitrogen, this hydrogen is still going to be attached to it. So the zwitterionic form, or where you have a negative charge and a positive charge that balance out overall to 0, is the form that's going to predominate in the human body. So in the human body, serine is going to carry a charge of 0. Now let's talk about its R group. So the R group of serine is pretty simple. You've got a carbon, you've got an oxygen with a hydrogen, so this is an alcohol group, and then this carbon is also going to be attached to 2 hydrogens here. This oxygen is going to be polar, so this is going to be a polar bond. This oxygen is able to do hydrogen bonding with other molecules, so this R group for serine is considered a polar molecule. And because this is polar, this is also able to do hydrogen bonding with other molecules, including water, which makes it hydrophilic. Serine is not an essential amino acid. You don't need to eat serine in order for it to show up in proteins in your body. Your body can use other molecules from other processes, including glycolysis, in order to make serine. So serine is not an essential amino acid. Serine is used to make other amino acids. So it sets up other amino acids not being essential as well. Serine also sets up nucleotide synthesis. So if you're trying to make any of the other nucleotide bases, like adenine, guanine, cytosine, uracil, thymine, you can use serine in order to set up making some of those as well.